Hello everyone, I'm Vikram. I'm a graduate student at Columbia University. So we have divided into two parts. The first part would be handled by Sarthika and then I'll take over.
Hi everyone, I am Sarthika. I am a software engineer at Microsoft, and today we are going to discuss about differential privacy and how to leverage Python's PyDB module for it. Let's first quickly go over the agenda. So first we will discuss few concepts of privacy, which are there are three key concepts of privacy. First we will be going over that and their definition. Then we will be seeing what are the risk of handling customer data, and then we will be going on to why don't we simply anonymize data and what are the problems we can face by if we try to just simply anonymize the data. Through this, we will move on to differential privacy, and it's mathematically defining differential privacy and how it works. We will also discuss two key types of differential privacy, and finally, we will move on to actually seeing how PyDB works with the help of code snippets, and we will conclude the presentation with a fun trivia and a Q&A session. Yeah. So privacy is basically the ability of users or a group of users to seclude information about themselves in a way so that they can selectively express themselves. So you can understand it as the ability to control how information about you is processed, stored, or shared. You should not confuse privacy with security. Security is basically who can access your data, while privacy is when and how can they access it. So there are three major concepts of privacy. First is identifiability. It's basically the extent to which a user can be identified with a data set. And then there is linkability. It's basically how, if there are if two or more data records can be used to identify information about a user. So if, for example, there are two databases and a user is present in both the database, we can use maybe their name to link those two databases and get a comprehensive profile of that user. So this is known as linkability. And then there is traceability. So traceability is basically tracing the origin of the data and who accessed it, when it was accessed, and for what purpose. So a very basic example which you might be familiar with is the use of cookies while browsing sites. So cookies can contain sensitive information like name, gender, and age, and the websites that have access to these cookies can easily access your data. So this is a very common example of how your data can be accessed. Now there are a few common attacks that are possible, like privacy attacks that are possible. We will discuss a few of them here. The most common is information leakage. It's basically gaining unauthorized access to your data through security vulnerabilities in the system or the model. And then there is a snapshot attack in which attackers try to take snapshots of the model at certain intervals and then combine them to launch an attack. Then there is a membership inference attack in which attackers try to manipulate models' output to see if a particular customer's data is present or not in that model. And there are other attacks like adversarial attacks, model stealing, and model poisoning. Like for brevity, we won't be discussing them. But yeah. Okay. Now, you all might be thinking, why don't we just simply anonymize the data? Why don't we just remove the information that we don't want to get leaked? So let's see why that won't help with the help of a case study. So there is a hospital that is maintaining record of its patients, and these are the fields that the hospital is maintaining. You all might think that we can just redact name and SSN, which are private to users, and publish the other records. But what if there is another data set, which is a publicly available data set, which is containing the voters list, all the persons who are having the voter right? You will see that there is this zip, birth date, and sex. These three fields are common in both the data sets. So using a combination of these, we can easily identify a particular user. This was in fact a true incident in which some politician's data was leaked because the combination of zip, birth date, and sex was unique for him. And so this is possible. Linkage attacks are possible in which even though you redact information, but there might be some other data set available publicly through which your a user can be identified. So why don't we anonymize data? So first is like, it might be possible that you are redacting the fields which are actually required for analysis, and it might render the dataset useless if you remove them. Second is the linkage attack, which I just explained with the case study. And third is, if the dataset is large, you can like fire multiple queries, and there might be a sequence of queries through which you can identify a pattern in the dataset and identify a user. So these are few caveats of just simply anonymizing the data. Now I would like to hand it over to Vikram.
Thank you. So let's come to the core concept, the core topic of our talk, which is differential privacy. So what's its goal? How is it defined? And what's under the hood? So what basically differential privacy aims is that it's a mechanism by which we address the paradox of learning nothing about any particular individual while still learning multiple things about the population in general. So if you think about any machine learning algorithm, your goal is basically to learn something about the population, like predict, like say, for example, given symptoms, if the patient has a disease or not. So that's our goal, but we still do not need to know if any particular individual in the data has a particular disease or not. So that's the goal of differential privacy. So if you do not abide by certain rules, you might, like if you query the data set again and again, there might exist a sequence of queries in which you can basically pinpoint that a particular user or particular point in a data set has that particular disease. So the goal is to make sure that statistical analysis is possible without compromising privacy. Then when I say query, a query is any function that I can run over the database. So it can be like, what's the average age of all the individuals in the data set? So I'll still be able to answer this question without asking, say, what's the age of Alice? So that's my goal, and that's what a query is. And what I mean by privacy is, so if I have a data set, and if I have a very similar database with me, if I run a query on those two databases and that query gives me a result, so if I look at both of these results, I should not be able to tell that if any particular individual has any particular attribute. So to go into more detail, let's see what's under the hood. So imagine the same situation. I have a data set with like say 100 individuals, and I have an algorithm which tells me, like a machine learning algorithm you can imagine, saying what's the probability of a person having cancer. Now if I have another similar data set in which one particular individual is taken out, so that's what we call as adjacent database, because it's almost the same except for the presence of one individual. I have the same algorithm. I run the queries on both of these data sets, and I have one particular result for each of those. So if any adversary is able to look at both of these outputs and then pinpoint what a particular individual has any attribute. So for example, if Alice has cancer or not, for example. So if that is true, then we say that the algorithm is not differentially private. So it's a property of an algorithm, not the property of the data set. And with the help of differential privacy, we can ensure that both of these outputs are indistinguishable, and so you would not be able to identify any particular user data. So now comes the complicated part of actually defining it mathematically. So so far we have just discussed like what's the goal, but it's very well mathematically formulated in this definition. So you would see there are two parameters, epsilon and delta. The epsilon parameter is what we call as the privacy budget, and the delta parameter is what we call as the information leakage probability. So I'll just read out the definition and then I explain it in a bit more detail. So it goes like this: for all pairs of data sets D and D prime that differ in a single participant, so something like this, and an algorithm M. This algorithm can be anything, but we define M to be epsilon delta differentially private if for all S is the output of my algorithm, so all possible outputs of my algorithm, if the probability that the output for the first algorithm is in S is less than equal to e raised to epsilon of it being in D prime, and with a delta parameter added in top. So what this does is, so to put it simply, like if I have a data set in which it predicts whether a particular individual has cancer, so that's my algorithm. Then I take another data set in which I add a particular user's data, and then so if in the first case, the probability of given a symptoms is like say 50%. If I add any particular individual's data, say Ross, and I run the same algorithm, and if suddenly the probability jumps to 80%, I'm almost certainly sure that that particular individual has cancer. So what this does is that the ratio of both of these probabilities should be less than e raised to epsilon. So that's my goal. So I should design my algorithm in such a way that removing any particular individual would not like suddenly spike up the probability so that I know something about an individual. So that's what the epsilon is, but there's another parameter called delta, which is the information leakage probability. In most cases, you would see like delta is also 0. So in that case, we define like epsilon differentially private algorithms. But if like the delta parameter is an additional parameter in which you can almost abide by the epsilon parameter, but we still add up information leakage probability. I've also defined the like official like what epsilon, delta, and m and s would be, but yeah. So now, as Sarthika mentioned, there are two approaches to differential privacy. So we'll go one by one. So local differential privacy is it's basically like how do we store the data. So in the local differential privacy, what we do is each individual data record itself is kind of changed. So you would see like there are 3 records, and we add some noise. We add some noise to all of these records and store it in a central database. So this is the local approach that we are actually tampering or like enhancing the security for each individual record and then storing it. In this case, the data store is itself untrusted because we do not store the original data. And in global differential privacy, what we do is we still store the data as it is, but then while anyone is querying the data, we actually compute the result of the query, but then we add some noise to the result of the query so that we still do not leak anything. In this case, the data set itself or the database itself is trusted, but like we still have untrusted aggregators or untrusted entities which are trying to query the data. So there are some algorithms and mechanisms which differential privacy demands. So algorithm is basically you have a data set, and on the left hand side, the list that we have is all the sorts of algorithms that PyDP supports. So PyDP is a module for exercising differential privacy in Python. So these are the algorithms supported. So bounded mean, bounded sum, bounded standard deviation, and so on. So what these algorithms do is compute the sum, mean, standard deviation, etc. of the data set in a differentially private manner. And then, as I said, in this, we add some noise to either our query result, or either our data. So these are the 3 different kinds of noises we can add: Laplacian, exponential, or Gaussian. We can mathematically prove that adding these types of noises. So I just want to emphasize the fact that these are not like random noises that we add on top of the data. These are very well mathematically formulated. So we can mathematically prove that if we add Laplacian noise or exponential noise or Gaussian noise, we can still abide by this definition that we have here. So these are all the 3 types of noise that we can add using PyDP. Now let's look at the interesting stuff that is actually going to the code and see how a differential private algorithm looks like. So what we are trying to do here is that we have a data set with the salaries of some particular individuals, and we are trying to find the sum and mean of their salaries. Now, if you imagine, if I do not abide by differential privacy, what I can do is, if I want to find out the salary of Jeff, for example, I do a sum of all the salaries. I do a query of like give me the sum of all the salaries in the database. It gives me a number. Then I remove Jeff from the data set, and then again do the same query. I take the difference, and then I know the salary of Jeff. So this is like very naive, but with differential privacy, what you can do is, with PyDP, I mean, what we can do is we can define, so we'll go one by one. So the first few lines are just importing, and then we imported like the bounded sum and bounded mean of like these 2 algorithms. Then we load the data set, we pre-process the data set, and this is what we have finally. Then we define epsilon and delta. So these are some random values for now, but we can change it accordingly. Then we do a bounded mean and bounded sum. So what this does is basically it adds Laplacian noise, because that's what we have imported from here. We have imported bounded sum from algorithms.Laplacian. So these few lines set up our differential private algorithm, and then we actually add the noise by using dpSum.quickResult. So what this does is it gives the sum of all the data set, but it's not the exact sum. It adds Laplacian noise on top of the sum, and then gives you the result. In similar way, we have the dpMean.quickResult. So basically what quickResult does is it takes the variable dpSum or dpMean, which is what we have set up in the previous step, and we have added Laplacian noise, and then it actually adds the noise and then gives us the result. And so we no longer have the exact sum and exact mean, we have the noisy sum and noisy mean, and then we just print it out. So yeah. So I again want to emphasize that we have imported Laplacian noise, but we could as well have done like Gaussian or exponential noise in this case. Now we, like, for the machine learning enthusiasts or like machine learning practitioners, we also have support for multiple machine learning algorithms in PyDP. So ironically, we have chosen the naive Bayes algorithm as a complex example, but basically I just wanted to also emphasize that we have support for algorithms like these as well. So again, this is an algorithm, and this is a code snippet in which we compute the accuracy of like a data set. We basically use the same API as sklearn, for example. We fit, the classifier itself is called Gaussian naive Bayes, and we import it from the PyDP library. We have a bunch of algorithms here. We have a set of epsilons that we run on, and for each epsilon we calculate the training and test accuracy and like get the results. So this is just an example to show that we have support for machine learning algorithms in PyDP. Now let's look at the things to consider while, so this was all about like how to write differentially private code. So it's still a very active library, PyDP that is. We still have not added support for a lot of things, but there's active development going on. So some of the things to consider is like using differential privacy is not absolutely necessary. So there are some problems in which you would not want to use differential privacy. For example, if there's a bank and it's trying to figure out if a particular transaction is fraudulent, it still needs to know the exact transactions of a particular user. It cannot just look at the aggregate results of users. So when there's individual level analysis required, you cannot use differential privacy, or you should not use differential privacy. If the data is small enough, then still using differential private algorithms won't make sense. It won't be useful as such. Then no epsilon is one size fits all. By that we mean that you actually have to do experiments with a bunch of epsilons to see what works best for your data. Then the next one is not understanding the sensitivity of your data. So sensitivity is defined as like, what if I change some parameter in my data set, and how different the algorithm output is. So by not understanding sensitivity, we might use the wrong epsilon or wrong delta values, which would result in like my algorithm not being useful at all. So it might just output random values by adding noise. Choosing the wrong DP algorithm, again, like it depends on what kind of noise you want to add. We have a bunch of choices. So all of these things basically point to like you need to research your data set enough so as to use the right DP algorithm, the right epsilon values, and the overall like which noise to add, which algorithm to use, and which epsilon to use. Failing to properly evaluate the accuracy of your result. So because we're adding noise, we can expect that the accuracy would not be the actual accuracy of your algorithm, because you're adding noise in the way either you store or the way you query the data. So you need to do a bunch of experiments to figure out the original accuracy of your data. So one more thing which I want to emphasize is when we are adding noise, basically for one query, it would result in like not exact result, it would be a noisy result. But overall, the mathematics points to that if we do a bunch of queries, we do a bunch of results, bunch of queries on our data set, all these noises would cancel out, and we would still be able to learn the overall aggregate property of a data set that we want to have. So now, because we do not have a lot of time, I would like go through the trivia questions, and like these are all yes/no questions, true/false questions. I would just like display the result, but yeah, we'll go through each question one by one. So, can differential privacy be applied to machine learning algorithms? The answer is yes. We already saw one example of Naive's algorithm. Does differential privacy provide perfect privacy protection? The answer is no, because it's bounded by parameters epsilon delta. So the way you use epsilon and delta values changes on how private your algorithm is. So that's why epsilon is called as the privacy budget of your algorithm. Is it a new concept? So personally, I did not know about differential privacy for a lot, like during my undergrad, for example. But it was like, it has been around since 2006. There have been a lot of very good books and active research. It's a very active research area and has been since 2006. Does differential privacy guarantee that an individual's data will never be exposed? So again, it's not a very strict guarantee, but you can still limit the risk of exposure. So in an ideal world, every user should be able to define the epsilon value or the privacy budget of that particular individual, but it's like a lot of time away, and we are nowhere close around that. Then does differential privacy require data to be fully anonymized? Obviously, like as we see, we do not need any anonymization. We can still keep all our attributes, but add noise and use like epsilon values accordingly. Can differential privacy be applied to non-numeric data such as text or images? So there are algorithms. So right now, what we saw is like the salary data set, for example. These are all numerical. You might see that we can add Laplacian noise, we can add random numbers. But there is support for data sets such as which contain text or images, and we can add noise accordingly, and our differential private algorithms would still work. Does differential privacy, I believe this is the last one. Does differential privacy allow for exact queries to be made on the data? The answer is no. We still get noisy results and noisy outputs of our queries, and it allows for approximate queries with a control on the amount of error that we can allow. So that was all for our talk. We are happy to take questions. Thank you.
Thank you very much. Okay, so I'll read out the questions that we have. So the first one, can you simply decide you need to add some noise to data, just rerunning the algorithm? Should I read it out again?
Yeah, yes.
Can you simply decide how you need to add some noise to data, just rerunning the algorithm?
Yeah, so basically experimentation, as Vikram mentioned, experimentation is like an essential part of this. So yeah, you have to like experiment and try which fits the best.
I would like to add one thing, like the noise should be mathematically sound, so we should add either like those three types of noises that I already mentioned: Laplacian, Gaussian, or exponential.
Okay, great. The next question. In the global noise approach, is noise added to each record or to a sample of records?
It's for each record, because we do not want any particular. So you can still control how much noise to add, but it's added to each individual record in the data.
Okay, thank you. The next one. Can differential privacy be applied to the exploratory data analysis phase of a project when the aggregation are not clearly defined yet?
Can you repeat it?
Should I read it? Okay, great. Can differential privacy be applied to the exploratory data analysis phase of a project when the aggregation are not clearly defined yet?
Okay. I think you can still not use differential privacy in the exploratory phase, but then once you decide the algorithm you want to use, say what machine learning algorithm you want to use, you can use it in a differentially private manner, which would still protect the privacy of each individual record.
Okay. The next question. Can noise possibly ruin the integrity of the data? How do you decide the parameters and the function of the noise? Is this a trial and error situation?
So basically, as Vikram mentioned, we have to add a particular like mathematical noise. So it won't affect the data because it would eventually the noise would aggregate and give the correct results. So that is why choosing the right type of noise is an important part in this. And what was the follow-up?
How do you decide the parameters and the function of the noise? Is this a trial and error situation?
Yeah, it's more like you need to try different values of epsilon, different algorithm, different noises to get to the correct. Like it's not one epsilon fits all. You have to like decide it for your own data.
The next question, would DP replace homophobic encryption, or would you say they are complementary techniques? Homomorphic, sorry. Sorry. Homomorphic encryption.
I am not aware of this, to be honest, sorry.
Okay. What is necessary to research about the data before adding the noise to data? What is necessary to research about the data before adding the noise to data?
Yeah, I would say like the most important thing is like if you try a bunch of queries and you have a particular privacy budget, for example. So if you see that adding a particular noise or using a particular epsilon value like gives very different results, or for say the data is very small, that even adding a small amount of noise actually can lead to like identifying individual records, that would not work. So it's like you need to experiment a lot, and maybe like there are like guidelines on what the epsilon value should be. So in most examples that I see, it's 0.01 or 0.1, which works for most of the average size data sets that we use. But we still need to do experiments to actually like pinpoint to a particular value.
Okay, great. So does anyone else have any other question? Thank you very much.
Thank you.